Hi, this is Mrs. Butcher here, and this video is over translating exponential graphs. And as a reminder from yesterday, we learned that exponential functions are in the format y equals b to the x power, where b is any number greater than 0, but not equal to 1. And let me remind you what the parent functions look like. We have our exponential growth parent function that is any letter b raised to the x power. When we raise anything to the 0 power, we get 1. And then if we raise anything to the 1 power, we get whatever it is, so b. And then that line, or that curve, actually grows and grows and grows exponentially, and it goes this way. But it's approaching a line that we call an asymptote at y equals 0. It never actually touches it. And our domain is all real numbers, but our range is from 0 to infinity, non-inclusive. Our exponential decay function is the same thing, y equals b to the x, only b is some number between 0 and 1. So now when we raise b to the 1 power, or to the 0 power, we still get 1. When we raise b to the 1 power, we're going to get b, but b is less than 1, so it's going down. And then the higher the power, the lower your result, but it does approach an asymptote here too. And by the way, whenever you graph any of these exponential functions, you must always draw in the asymptote as a dashed line. And then if you go the other way, if you take a fraction and you raise it to the negative 1 power, we're taking the reciprocal, so it actually is getting bigger to the left, but it's coming down from left to right, and that's exponential decay. Your domain is all real numbers. Your range, same thing as with growth, 0 to infinity. Those are the parent functions. But today we're going to talk about what happens when we translate them. And it's the same translating rules that have applied to the square root functions and the quadratic functions and the absolute value functions and every other function that we've looked at this year. So for any exponential function, see, here's our b and here's our x power. But we could stick a minus in front of it, and that would reflect it over the x-axis. We could have a number in front of the number that's raised to a power, so note that a is not being raised to the exponent. A is separate, and that will be your stretch or shrink. Or another word for shrink is compression. We could have a plus or minus a little number up there in the exponent. So whenever it's with the x, just think about when it was with the x in the radical or with the x inside being squared. That's your horizontal shift, and it's the same as it always is. It's opposite of what the sign is. And then you could be adding or subtracting something at the end. And just like always, k is our vertical shift. And there is one more thing I want to add to this one, which is actually true of all functions, but we just hadn't talked about it before. If the x itself is negative, that will be a reflection over the y-axis. So your graph would go from looking like that to that, or vice versa. So now let me do a couple of examples for you. The first one we're going to do is graph y equals 1/2, and then in parentheses 4 raised to the x plus 2. We'll always have our b value in parentheses if there is an a. So keep that in mind. We can't half that 4 and make it 2 to the x because the 1/2 is not being raised to the x power. So what we're going to say is, okay, it's positive, so it's not reflected over the x-axis. Our a value is 1/2. That's less than 1. So this is going to be a vertical compression by a factor of 1/2. The exponent x doesn't have anything with it, so it's not shifted horizontally, but we do add 2 at the end. So that's our k value. K is 2, which is going to be a vertical shift of 2 units. And all of these things are happening to the graph of y equals 4 to the x. That 4 doesn't affect anything. The parent function was y equals 4 to the x. That was our parent function. So the 4 doesn't make it stretch or shift or shrink or anything. It doesn't do anything. The 4 is from the original function. And I know that's hard to remember. The one on the outside is your stretch or shrink. The one on the inside was your original. So you just leave that 4 alone. It doesn't affect anything. So now to graph it, let's make a table. But before I do that, I want to think, okay, this was my parent function, y equals 4 to the x. That always has an asymptote at y equals 0. If I shift it up 2, my asymptote is going to shift up 2 as well. So that's the first thing I'm going to draw in. And if you're asked, what is the asymptote? Remember, it's a horizontal line. It's going through y equals 2. And that's the equation of the line. The horizontal asymptote is at y equals 2. You have to say y equals 2. You can't just say 2. All right, so I'm going to start with 0 for x because that's the easiest one to plug in. And if I say 1/2 times 4 to the 0 and then plus 2, we need to do the math somewhere. You can use the calculator, you can do it out to the side, but if we have half of 4 to the 0 power and then add 2, 4 to the 0 is 1. Half of 1 is 1/2. 1/2 plus 2 is 2.5. So 0 and then 2.5 right there. All right, then we'll have the point, we'll plug in a 1 for x. So half of 4 to the 1 power. Half of 4 to the 1 power, that's half of 4. Half of 4 is 2, and 2 plus 2 is 4. So we have a point at 1/4. You could plug in a 2. Half of 4 squared. 4 squared is 16. Half of 16 is 8, and 8 plus 2 is 10. So we have a point at 210. And that's as high as I can go on here. So that gives me enough to show me what the graph's doing on the right. Let's look on the left a little bit. If x was -1, then we're doing half of 4 to the -1 power and then plus 2. And remember, anything to the -1 power means the reciprocal. So we're doing half times 1/4 plus 2. And half of 1/4, remember, when we multiply fractions, we do top times top and bottom times bottom. And 1/8 plus 2 is 2 1/8. So we went from 2.5 down to 2 1/8. And it's just going to keep going 2 and a fraction smaller and smaller and smaller, but it will never actually reach 2. And so these points are plenty. Draw your curve approaching the asymptote but not touching it. And then tell me the domain and range. So the domain of this, we could plug in any x we wanted. It goes from -infinity to +infinity. And then our range, the lowest value is 2, but it doesn't touch it, so non-inclusive, going up to infinity. All right, our other example that we're going to do, we're going to graph y equals -2, and then in parentheses 1/3 raised to the x minus 1 power. So we want to first identify our parent function, and that's this right here. Whoops, didn't mean to go through the x, but it's 1/3 raised to the x power. Then the negative out in front tells us that the thing is going to be reflected over the x-axis. The 2 out in front tells us that it is going to be stretched by a factor of 2. And that little -1 up with the x in the exponent is our horizontal shift. And remember, we always go the opposite of the sign, so we're going to shift it right 1 unit. Okay, so for this graph, I know that with my parent function, the asymptote is always at y equals 0. And then this one has not shifted vertically at all, so our asymptote remains at y equals 0. And the first thing you should do is draw that on there. Remember, once again, it's y equals 0. It has to be y equals, not just 0. So we've got that drawn on there. Let's make a table for the rest of the values. All right, always start with 0. When x is 0, we're going to have -2 times 1/3 to the 0 minus 1. So that is the same thing as saying -2 times 3 over 1, because that's -1 power means reciprocal. -2 times 3 is -6. So 0, -6 is going to be our first point here. Right there. Alright, we could plug in a 1. And when x is 1, we've got -2 times 1/3 to the 1 minus 1, which is 0 power. Anything to the 0 power is 1, so we have a point at 1, -2, which would be right here. We could plug in a 2. we'd have negative 2 times 1/3 to the 2 minus 1, which equals 1. So I have negative 2 times 1/3 is negative 2/3. So at 2, negative 2/3 means going down almost 1, 2/3 of the way to 1. And that's enough points to see that it is approaching our asymptote, and then you know it's not going to touch it. So if you draw it skimming the asymptote, you're good. On the other side, we could plug in a negative 1 for x, and that would be negative 2 times 1/3 to the negative 1 minus 1. So this is tricky. This is negative 2 times 1/3 to the negative 2 power. Remember, negative exponent means reciprocal, so it's negative 2 times 3 squared. And so 3 squared is 9 times negative 2 is negative 18. And that's way down here. Actually off my grid. I tried, but didn't get it on there. So when you draw it, you can just draw it approaching, but it's not. It's going to hit negative 18 like down here at the bottom. I think right there, if I can reach that. All right. So there's your curve. And then if I ask you for the domain and range, our domain, all x's are okay. It looks like it's approaching an asymptote here, but it's not. It's still going to the left. It's just slowly going to the left, but it's still going to the left. So negative infinity and then positive infinity on the right. You arrange the lowest y value. Some of you are still having trouble with this. The lowest y value is negative infinity. And the highest y value is up here at the top at our asymptote, y equals 0. And it doesn't touch it, so we have to put a soft bracket on that. So that's a couple of examples, one of growth, one of decay, that have been translated. I hope that you guys get a good idea of what's going on. Make sure you ask me questions in class tomorrow if you have any, and we'll go over a couple more examples in class tomorrow and do some practice problems. And I'm running out of jokes, but here's an oldie but goodie. I'm sure you guys have seen this before. All right, have a good night.